Welcome back everyone. In the last lecture we had solved the quad rotor problem, altitude control problem for a quad rotor using the CHD toolbox in MATLAB. We fine tuned the controller so that we could reach the exact specification that we wanted to get. Today we take up the other problem as promised. The problem statement was, given a unity negative feedback system with the open loop transfer function of this form, determine the value of k such that we achieve 40% overshoot and 2 seconds settling time for unit step input. Of course, the input can be some other step also, but for a step input. Now, if this is the problem statement that we have and we saw that this we were not able to solve, the reason being that the desired pole location was located at a point where the root locus was not passing through, right. And like I told you in the previous lecture itself, that if we want that the root locus has to pass through the desired pole location, we will have to change the shape of the root locus, which means we can no longer go with a gain block k here, but we have to change it to something else. So, like in the previous case, if I introduced a 0, say, if I introduce a 0, if I change the controller to k into s plus a, will I be able to solve the problem? Let us see. If I introduce a 0 here, we know that what will happen to the root locus? The 0 will act like pulling the branches towards it, right. So, the root locus will look something like this. Okay. So, you can go ahead and check what the root locus will look like. By now, you should be able to draw this rough sketches of root locus on your own. You do not even have to go to the rules, it should quickly come up to you as to how it will look like. So, in this case, this is how the root locus will look like, and if that is the case, there is no way that this branch is going to go towards that direction. You can look it up using a simulation also. In this simulation, you can see that I am changing the position of the 0 here. You can see that I am changing the position of the 0, and in no way when I am changing the position of this 0, the root locus is going to pass through this point. Okay, because this point exactly lies on this -2 line, and so the root locus cannot go in that direction because the 0 is pulling it towards itself. Oh, you can always argue, why don't I put a 0 here? So, see, if you put a 0 here instead of this point, then what will happen? You see, these are my open loop poles, then one of the branches will go in that direction and the other will come in this direction. So, then there will be no branches on the complex part, right, on the second or the third quadrant, right. So, in that case also you will not be able to pull this off. So, that means I have to use a pole maybe. So, let us see if a pole will help us. Now, with a pole, am I able to solve this problem? You see, with a pole I will be able to solve this problem because the root locus will pass through this point now, right. You see the root locus, if I keep on changing the position of the pole, you see that there will be a point at which the root locus will pass through that point. Yeah. So, we can come up with this 25.07 approximately. At this value the root locus does pass through that point. Okay. So, we can go ahead and, like the previous case, we can solve this problem by finding out the value of a at which the root locus will pass through that point. So, if we have to do that, we go for the angle criteria. So, by the angle criteria, these will be our angles. So, this is tan inverse of minus of tan inverse of 6.8572 divided by a minus 2 here, and then we have tan inverse of 6.8572 by 4 minus 2 here. So, these two angles will be that, and from here we have minus pi by 2. So, the sum of the angles in this case will come out to be must come out to be minus 5, and then if you solve it, you will get a equal to 25.5106, which is approximately what we were also seeing in the simulation, but exact value will be 25.5106. Once we have the value of k, you know what to do now. You have to go for the magnitude criteria. Now the magnitude criteria, so what is the open loop transfer function? K into this multiplied by this. So this is the open loop transfer function. Evaluate that at minus 2 plus 6.8572. So this is just at plus you can evaluate, even at minus is also fine. So once you evaluate it, K comes out to be 1199.5. So finally, if you go ahead and use this transfer function, okay. So once you have used this transfer function, you can see that, so G is this, C is this, closed loop transfer function, pole 0 map if you see. So you see the poles, location of the poles, these are our desired pole location, okay. So this we have achieved the desired pole location, and this is the third pole. Now this third pole is 10 times away from these two positions. So what does this mean? This means that in this, see, there are no zeros also here. So that means since the third closed loop pole is 10 times away from these two poles, these will act as dominant poles here. These are your dominant poles. This is what you wanted. That means the response will depend only on these poles. That means this will have this so second order approximation in this case is valid. So which means whatever we have designed, we should be able to achieve using these poles. So let us see. If we look at the step response, let us see how the step response looks like. The step response of this closed loop system. So right click on this characteristic and then you go to settling time. You see 38.5% and 1.96%. So we had, our objective was 40%, right. So we are able to achieve 38.5%. So 40% was our objective. Here our objective was 2 seconds, okay. Approximately we are able to achieve that. Of course you can fine tune it and then get to 40 and 2 seconds like we did in the previous case. However, there is an issue with this response. This looks completely fine, right. I mean, this should work. The steps that we have followed is almost similar to what we did in the last lecture also, right, for the quadrotor example. Only thing is that now there is no zero, but there is a pole now, open loop pole that we are introducing, so that the root locus passes through those points, the desired pole locations, the locations we want to make, the locations which we want to be dominant poles. But the issue is, look at the final steady state value. So what is the steady state value here? You see the steady state value here is not 1. See, when I found out step response is the response of the system when you give unit step input to the system. But you can see that in this case the output is not 1. So that means there is a steady state error here, right. If you draw a line here, this is the one line. So there is a steady state error here. We have not taken care of that. See, this was not explicitly told, but of course if you want that the output should follow your reference and your reference is 1, so the output should have been 1. If the reference is 1.5, the output should have been 1.5. That is not happening in this case. So we have some issue here. I mean, of course it solves our two the performance specifications given were catered to, but remember I already told there are two hidden specifications always. One is stability, the system, closed loop system has to be stable, and the second one is that the steady state error should be 0, right. Otherwise the desired, you will not be able to reach to the desired location. So we are at a point where now we have to think of something else, okay. Remember, if you are fine with steady state error, it's okay, forget about it, okay. But in most of the cases you won't be, okay. So you won't like the steady state error should not be there. But if you are fine with steady state error, your problem that you are tackling does not have anything to do with steady state error, or the steady state error is so small that you can neglect it, it's fine, it's up to you, up to the, of course, the problem statement, okay, or the system that you are designing. However, we would like to get rid of the steady state error. Now how do we get rid of the steady state error? That is the problem that we have, okay. So what type of controller should I use here so that I can get rid of the steady state error? Let us think about it a bit. Now you see, when you had introduced the pole into the system, the pole was something like this, right. This was what you did. So you replace it by k by s plus a, whatever value of a and k came, I mean some value you got and you used it. Now if I ask you what is the type of this system, remember how do you find out type of a system? To find out type of a system, you have to find out the open loop transfer function of the system. In this case, the open loop transfer function will come out to be k by s plus a whole into s plus 2 and s plus 4. Of course, the value of a and k you already know because you have already designed the system, designed the controller. Okay, you have to put those values. Now, the type of the system in this case will be 0 because there are no poles at the origin. There are no poles at the origin for this transfer function. So, the type of the system is 0, and we know that for a type 0 system there will be steady state error if you give step input, right. So, that is why we are seeing a problem, we are seeing a steady state error at the output. So, which means that I have to somehow make it a type 1 system, at least more than 0. It has to be either type 1, type 2 or whatever, but it cannot be type 0. So, one thing that you should get from this point is that I have to somehow introduce a 1 by s into the system. So, there should be a 1 by s and then there should be some other transfer functions here. So, that this 1 by s will take care of the steady state error because as soon as I make it 1 by s comes in, so it becomes a type 1 system, and this part of the transfer function will take care of the transient part or basically the specifications that we wanted to handle, 40% and 2 seconds. Remember, as soon as I put 1 by s, no longer the root locus remains the same, the root locus has changed now. So, what should I introduce here also is a question. So, what we are going to do now, we are going to do this entire problems from scratch in the CSD toolbox that we have seen in the last lecture. In the last lecture, the methodology was analytically we came up with a controller. The controller was not giving us the specification that we wanted, it was off by some 7% or something if I remember correctly, and then we went to CSD toolbox and then fine tuned the controller so that it gets to exactly where we wanted to. In this problem what we are doing is we are going in blank. The only thing that we know is that we will introduce a 1 by s here. So, the controller will look something like ks by s, something like this. Now, what will be the other things we do not know. So, let us go ahead and try to see how does the CSD toolbox help us in this case. So, the first thing is that we have to define the transfer function. The transfer function is g equal to 1 by s plus 2 into s plus 4. This is the transfer function. Okay. So, this is the transfer function, s has to be defined here. Yeah. So, this is the transfer function that we have. Now, like the previous case, we go to apps, we go to, remember here I have not defined C, okay, because we want to do, I am doing it from scratch. So, I do not know what C would be. So, again Bode plot I am not concerned about. So, let me just cut that, then go to edit architecture. So, now only G I am specifying. So, G I am specifying, I am importing, okay. So, this is the G that I have, okay. Right now you can see F is 1, C is 1, G is 1 by s square plus 6s plus 8, that is the transfer function of the plant, H is 1. So, this is what we have. Now, let us look at the specifications. So, what are the specifications? You go to step response, right click, design requirements, new. I will add the specifications now. So, what is the first specification? The specification was that the overshoot should be 40%. Okay. Now, here comes the other thing, settling time. Now, the settling time we wanted it to be 2. So, you see there will be a problem because as soon as I give settling time as 2, the rise time should be less than the settling time, right. So, that is why you see the rise time I have to give first. See, remember we in this question we have not taken rise time as a specification. So, you can give anything actually. So, let me give it 1, it should be less than the settling time, but settling time should be 2, okay. So, settling time is 2, overshoot is 40. So, I press OK, and as soon as you press OK, you can see this is the overshoot line in the step response. The overshoot line, this 1.4 line, this is the step response cannot go beyond that. This line is the rise time. I am not concerned about the rise time, but the rise time should be 1 second, but I am not concerned about that. So, let us not talk about that. Let us talk about the settling time. So, the settling time is this 2. So, 2 seconds is the settling time. So, within 2 seconds, the response should get inside this band. You can see this band. You can actually go ahead and see what this band looks like. You can see this band. So, this is a 2% band, that means it is from 0.98 to 1.02. So, this output here should get inside, the response should get inside this band within this 2 seconds, okay. Then only we will say that okay, we have got a valid response. valid as in we have reached our specification. So, just by using k am I able to do that? No, you see, by using k means I am changing the value of k, you can see this, right. So, you can right click and restore view to get to the original view. So, you can see I am changing the value of k, that as I change the value of k, the response is changing, but it is not giving me what I wanted, right. Is it giving me what I wanted? You see there is still steady state error, you can see, right. Even if I go to 40%, there is steady state error. That was one of the problems that we were facing. Okay. So, now what you can do is, let us go to the root locus. Now, we will change the root locus. Now, how do I change the root locus? So, in the root locus also you can go ahead and right click first. So, let me restore the views first, right click and restore the views. Now, on the root locus also you can put the design parameters that you have. So, you see, remember this hand is coming right now, you can see in the screen, you can go there and click on this. So, when you click on this hand, you can drag actually, if you left click and keep, you can change the position. I will just remove that now. Okay. This is the default, when the cursor is visible, this is the default mode where I have not chosen any of these tools actually. Okay. Now, on the root locus also, let me put the parameters that we wanted to achieve. So, if you right click on that, okay, go to design requirements, new, like the step response case, here also you can give the design requirements. So, the settling time we want to be 2 seconds. As soon as I give settling time to be 2 seconds, you can see that there is a line coming here. So, the settling time, you remember on the root locus, what is settling time? Settling time is 4 by zeta omega n, right. So, when you choose a settling time, you are actually choosing the real part component of the closed loop poles. Okay. So, this is that line, remember, and then right click, design requirements, new. I also need percentage overshoot, I want it to be 40%. Again, percentage overshoot is linked with zeta, right. From percentage overshoot you can get zeta. So, this will lead to a zeta line, and you can see this is the zeta line that you have. So, I want, that means from this what you can understand is that I want that my desired pole location should be at this point to get to 40% and 2 seconds. The intersection of the zeta line, this is the zeta line, zeta corresponding to 40% overshoot, and this is the zeta omega n line, the line corresponding to 2 second, the line corresponding to 2 second settling time. Yeah, fine. So, now you can see that the root locus is not passing through this point, which means I am not, that is why I am not able to get to that exact location. So, what should I do now? So, I will have to change this root locus. Now, remember what was one problem that we had? One problem that we had was steady state error. You can see that in the step response there is steady state error. So, I have to remove the steady state error, right. So, how do I remove the steady state error? You can, so first thing is that we will introduce a 0, we will introduce a pole at the origin. Remember, this is what we discussed, right. So, we have to introduce 1 by s. So, let us try to introduce 1 by s. So, if we introduce 1 by s, how do I introduce 1 by s? You go to the white part of the root locus, do not do it on the yellow part, because sometimes you might change the specifications by mistake. So, go to the white part, right click, and then you can see add poles and zeros. So, that means using this you can add extra poles and zeros into the root locus. Okay. So, I want to add a pole at the origin. So, if I want to add a pole at the origin, that is nothing but an integrator, because I am adding 1 by s. I have to add a pole at the origin, means I want 1 by s, and 1 by s is nothing but integration. Why? Because what is the Laplace transform of ddt of ft, s of fs, fs being the Laplace transform of ft. What is the Laplace transform of integration of ft? Fs by s. Okay. So, 1 by s multiplying 1 by s to a function is basically, it means that you are integrating that function. So, you can add an integrator. You will see as soon as I click on the integrator, there will be a pole introduced at this point. Okay. So, keep an eye on the change in the root locus. So, I am adding an integrator. You see, as soon as I changed it, you see an integrator, there is a pole at the origin, and you can see the output now. The output is like gone haywire. Why? Because you see, where is the k? The k is at this point, and this is exactly a point which is on the right half of the complex plane. So now we have closed loop poles which are on the right half of the complex plane. You can go ahead and drag this K to the left side, and then the output will not become unstable. Anyways, so now have I solved the problem? No, because this will take care only of the steady state error. This is not taking care of the, this is not taking care of other things, because you can see that output, I mean I am not able to reach to the specifications that I want to. Now comes the part where we will have to think a bit. Okay. So fine, I have introduced a pole at the origin. By introducing a pole at the origin, I took care of the steady state error. How do I ensure that I get to 40% and 2 seconds? Okay. So of course, if I have to do that, from the, look at the root locus. From the root locus, I know that the desired pole location should be at this point, which means that this root locus must pass through these points. That means I have to pull the root locus towards these points, which means I have to introduce a 0 somewhere. Okay. So let me introduce a 0. Right click, add a real 0. Okay. So right click, add a real 0. As soon as I click on this, you can see on the cursor there is a small dot there. So now the 0 is on the cursor and I can place the 0. Let me just place the 0 at this point. I will click on this point and the 0 will be added. And you see, as soon as I added the 0, you see the root locus has come to towards the right a bit. I hope up to this it is clear. Now have we solved the problem? Maybe, because I have put this 0 wherever I wanted to. So I can click on this 0, I can hold on to 0 and keep on changing the position of the 0 also, and I can change the root locus. You see, when I change the position of the 0, I am changing the root locus also. Now where should I go? I want that the root locus should pass through these points. So if I want that, I would like that my 0 should go in this direction, so that the root locus passes through that point. Now when will the root locus pass through that point? You can see that the root locus is passing through that point if I bring it very near to -2. Okay. And if that is the case, is the output showing correct output? No. Why? Because you see, where is the K? K is at some arbitrary point now. I have to click on K and change the value of K and take it to this point. Okay. So this looks like it is solving our problem. Okay. So let me just hold on to 0 a bit. The 0 has gone towards that side. So let me just, okay. Now you see, if I change, so this is where our output is correct. I am getting what I wanted to, right? You can see that 40% overshoot, the response has also got inside this band within 2 seconds. If you look at G, you see this is the G that you get. Okay. Looks like we have solved the problem, right? I mean, I have introduced a 0 and I have introduced an integrator also. Basically, I have introduced a pole at the origin also, and looks like we have solved the problem. Theoretically, yes, but there is an issue with this. The issue is that the 0 that you are introducing is very near to the open loop pole. Okay. So there is some kind of, there is a chance of what is known as pole 0 cancellation. Think about it. Okay. If I go back to the diagram that we had, suppose you introduce a pole, introduce a 0 at this position K S plus 2. Okay. So then what you have done is, you have basically, we have gone for this type of a design, right? 2 or 2.04, something like that. So if I find out the open loop transfer function, these two will get cancelled out, right? This cancellation is an issue. Okay. This will show up with some other problems when we look at it from a modern controls perspective of state space and all. So we try to avoid this. First problem is that, and second is, you might not even know where your open loop pole position is. Okay. In that case also, I mean, to get to this exact 0 will also become a problem where you are cancelling it out. Basically what you are doing, if you write this, you are completely changing the transfer function, open loop transfer function itself, right? You are replacing the open loop transfer function by 1 by s into s plus 4. Okay. So we try to avoid these type of issues, we try to avoid this type of cancellations. Okay. Because this leads to some other issues also, which we will discuss, what happens when pole 0 cancellations happen. Okay. But we will avoid this for the time being, believe me, we will try to avoid this. So now now I have again brought back the issue, right. I am not able to solve it yet, because I know that now, okay, now that we are saying that we will try to avoid this, that means with this 1 0 there is no way that I will be able to get the root locus to pass through that point. Okay. So, then what can we do? Now, you see what we can do is, let the 0 be here, I can see the root locus is, suppose the 0 is at this point. Now, I want that the root locus should further come towards the desired pole location, right. So, that means I will have to add another 0 now. So, right click and add another real 0. So, let me just add it here. Okay. Now, you see I have added 2 zeros now. So, I have 2 parameters to play around with. With this 0 I can change the root locus, and with this 0 also I can change the root locus. So, let us see how do I change the root locus. So, with these 2 zeros I can play around, and I can keep on playing around and find out the position where this will pass through the this desired pole location. You see, I can keep on changing these 0 locations. Remember, I mean, these 0 locations are in our hand, right. We can change this, because this is, we are designing this. So, see, by changing this I am able to change this. So, let me just drag it further. So, approximately now the root locus passes through that point, right. We can see that the root locus is passing through this point. Only thing is that now you see the step response is not matching what we wanted to, because the k value that we have chosen is not correct yet, because this this pink colored k values, or the points representing k, must come to this point. And see, as soon as it came to this point, you see now, look at the response now. Okay. Look at the response is again 40%. Have we reached 40%? Let us just check quickly. Yes, approximately it is 40%. So, right click. So, let me just bring it back to the original thing. Okay. So, this is 40%, and you see the settling here, the settling time also within 2 seconds we have reached the settling band. So, it seems we have solved the problem. Have we taken care of the steady state error? Yes, you see the output is at 1. So, the steady state error is 0. Why? Because of this, the addition of this pole at the origin. So, this is our controller. We have actually gone ahead and found out a controller which not only satisfies the specifications, but also takes care of the steady state error, and also it is stable, right, because the closed loop poles are on the left half plane. So, what is the C? Look at C. You click on C. This is the C matrix that you C controller that you have come up with. Okay. Let me write down this controller. So, the controller that we came up with is so 3.5265 S plus 10.25 multiplied by S plus 7.645 divided by S. Okay. And you see, these are the 2 zeros that we have introduced. And at the end we went to we corrected the k value, so that we get our responses as we wish. So, this actually goes ahead and solves our problem. Okay. We get the exact step response that we wanted to. Okay. Now, what I want you to do is, you take this transfer function and you go through those entire codes where we wrote down the closed loop transfer function, and then we found out the step response. You will get the same step response. Go to right click on it and see the peak specifications. You will get what we have found out. So, what we did basically, in the previous lecture we fine tuned the controller from the analytical values that we came up with. In this lecture we actually did this entire thing from scratch, right. We first understood what is our problem. We had a problem of steady state error. So, we used a integrator for that. We used this 1 by s, increase the type of the system. As soon as we increase the type of the system, the steady state error went to 0. For unit step, we know type 1 system gives steady state error 0. So, we made the system into a type 1 system, and then we introduced 2 zeros. Okay. With 1 0, we found that the problem was getting solved, but then there was this problem of pole 0 cancellations, which we wanted to avoid for reasons which will be clear later. Okay. But then with 1 0, still we were not able to solve the problem. So, I introduced another 0. Why? So that the root locus can be pulled towards the desired pole location. Now, all this I have done because it leads to something, okay, and that is what we will be discussing in the next lecture. So, at least I hope that in these 2 lectures you have understood how to use the toolbox, how to actually understand, interpret, how to think as to what changes I should do in the controller, so that the output gets changed or the root locus passes through the desired pole location. And the other important thing is you could see that there are 2 things going on in the design. One is steady state error and one is the specifications, the specifications like overshoot and peak time. Steady state error was also a specification, right? We always want that to be 0. So, that specification was taken care of when I introduced a pole at the origin, because I increased the type of the system. Whereas the 40% and 2 second specification, 40% overshoot and 2 second settling time specification was taken care of by introducing those extra zeros and then changing the value of k correctly to the point where the root locus, was passing through the desired pole location. So, there are these 2 important ideas. One part is taking care of the steady state response behavior, because the output, the steady state error is going to 0, which is basically that 1 by s that we have introduced, and the other part is taking care of the transient part, the part where the transient is in the beginning of the response, the starting of the response. Remember, we had talked about, we divided the response into 2 parts, transient part and steady state part. This is where it comes into play. Okay. In the next lecture, we will see that whatever we have discussed in the last 2 lectures give rise to what is known as PID controllers. Okay. So, we will discuss, I will introduce the idea of PID controller, and from there we will take it up next. Thank you.